Great. Okay, so as John mentioned, I'm going to talk about the use of gravimetric vapor absorption to characterize the catalysts, in particular one which are used for CO2 hydration reaction. Before I start, I would like to thank you all for dialing in today. We appreciate very much your time you're giving us. So I also would like to acknowledge my collaborators, Khalil Hassan and Lydia Schiller from School of Engineering at the University of Newcastle. These are the people who actually provide the sample and help this work to happen. So let's dive in. Okay. As you all know, one of the most discussed topics nowadays, except the coronavirus, is probably the rise of carbon dioxide in the atmosphere, which is actually one of the major factors responsible for increase of global surface temperature. As you can see from this plot here, the amount of carbon dioxide in atmosphere has been steadily increasing from 1950s, and the trajectory shows that it will carry on increasing unless we are going to stop it. Hence, multinational agreements, so the Paris agreements, have been made to control carbon dioxide emissions and limit rise of global temperature by 2 degrees. There are several sources of carbon dioxides, which are listed, shown on the slides here. So we have the energy sector, as we mentioned, mainly the fossil fuels, oil refineries, cement industry, iron industry. Now there are two main capture methods. One is the carbon capture utilization, and the other one is carbon capture storage to reduce the CO2 in atmosphere. Today, we are going to focus mainly on carbon capture storage, and in particular on mineral carbonation, which is very important. Mineral carbonation, for instance, geological storage, or the other storage options less is geological storage. So, the mineral carbonation process for carbon sequestration. So first, let's define what the carbon sequestration, which refers to sequesters or stores carbon dioxide in three soils, oceans, or in geological formation. So mineral carbonations involves reacting carbon dioxide with metal oxides, such as magnesium oxide, calcium oxide, to form magnesium carbonate or calcium carbonate. Here we see the actual typical reaction. The first step, there are 3 steps for mineral carbonation. The first step is carbonation. Basically, this is the process of carbon dioxide dissolving a liquid. For example, carbon dioxide is added to water under pressure to make it easy to drink. The second step is reaction of aqueous carbon dioxide with water or catalyst to form carbonic acid. This is a reversible reaction. Each carbonic acid can be transferred back to bicarbonate. This reaction can be actually accelerated by catalysts. So in this case, we can use either carbonic anhydride, hydrochloric acid, or boric acid. So they're typical catalysts. But the aim of this work today is actually to replace this catalyst using the nickel nanowires or nickel nanoparticle catalysts. The reaction rate or extent of the carbonation process is influenced mainly by the particle size, surface area, pH and steering rate, and temperature pressure. So the main goal of this work is to study actually these nickel nanowires and nickel nanoparticles in the silica aerogels catalysts and compare their performance between each other for the carbon dioxide hydration reaction. As I mentioned, so this is materials which are employed as the catalyst for silica aerogels. So nickel nanowires and nickel nanoparticles were initially synthesized by following solvothermal process. I'm not going to go into details, it was by chain. And nickel nanowires and nickel nanoparticles on silica aerogels were synthesized following the sol-gel process. As you can see on the left-hand side, we have the TEM image of nickel nanowires, which showing the wavy structure. And on the right-hand side, we look at the just silica aerogels and the size particles. Now we look at this material, this catalyst went through the characterization, traditional characterization processes like SEM, XRD. So we're going to go through these now. So now first, we're going to look at the scanning electron microscope images at different magnifications of nickel nanowires catalysts or silica aerogels. So SEM images of nickel nanowires composites confirms the mesoporous nature of the support. Estimation of the pore diameter from SEM images shows that the majority of these pores is in the range between 20 to 4 nanometer. So as you can see, this is clearly shown for 400 ppm nickel nanowires and 500 ppm nanowires. If you look at the 700 ppm nanowires, we can see, except of the mesoporous, we see also some macroporous, because you can observe the pores which are larger than 50 nanometers in this case here. Now, the other characterization of fingerprint techniques, which is generally used to characterize material, is X-ray diffraction. So here we look at the X-ray diffraction of silica gel nickel nanowires. So first you have this broad peak around 25 theta, which can be applied to amorphous silica. And then you have a 111 P, which can be assessed to nickel nanoparticles. So nickel nanowires, X-ray diffraction pattern at the bottom. Here's the nickel nanowires X-ray diffraction of in silica aerogel. So we just confirm the correct phase of the material of the catalyst was. The other characterization, as I mentioned earlier, we're going to look at the aqueous and gaseous characterization. So we start first with aqueous characterization. So it is liquid phase characterization, where we're looking at the pH changes during the bubbling of carbon dioxide through deionized water at atmospheric pressure and room temperature. So what you see here on x-axis, we have the time in seconds. On the y-axis, we have the pH. First, what we see here is the fact that the silica aerogel, which is this line in blue, shows no activity for CO2 hydration reaction at all. The strongest activity for CO2 hydration reaction shows pure nickel nanowires, which can be seen by this solid black line here. Now, when we look at the different composition of nickel nanowires in silica aerogel, what we observe, as the loading of the silica or nickel nanowires is increased, let's say from 400, 500 to 700, the catalytic activity for CO2 hydration reaction is increased. So the conclusion is more nickel nanowires is doped into the silica aerogel catalyst, better catalytic performance we are getting in Aqueous characterization. Now we're going to move to the main part of the talk, which is about the gaseous characterization. And gaseous characterization is basically refers to the vapor gas phase characterization, and this is going to be described by physics option process. So if you look at the scheme or typical physics option process, where you can vapor or gas molecule reacts with a solid surface of a material, and these this can form adsorb layer, and some of the molecule might diffuse into the bulk of the solid. As the pressure is increased, or relative pressure of humidity increases, more molecule gets absorbed into the molecule. And as you can see, the rest of the molecule does not get into contact with the solid material, they just can get out of the system. So this is the typical physics option process at thermodynamic equilibrium, where heat absorption is equal to heat evaporation at each isotherm point. Now this physics option process can be described by adsorption isotherm. So the adsorption isotherm is a relationship between the amount of gas or vapor absorbed against the equilibrium relative pressure. As you can see on this picture down here, the relative pressure is shown on x-axis, the demand adsorbed is shown on the y-axis. Now, what is important in x-axis is we have the ratio P over P naught. What does it mean? This is the pressure divided by saturation pressure of pure adsorptive at the experimental temperature. Now, during this adsorption process, so in this case, we look at the water adsorption on carbon, several phenomena can occur. First one, you have the we can have monolar adsorption, multilayer adsorption, condensation into pores, bulk absorption, and hydration reaction. Here we look at the type 4 adsorption isotherms. Now, this is 2 cycles. What you see, the light green and red is the adsorption branch for this sample. So the adsorption branch is characteristic by stepping up the relative pressure from 0 to 90%. And as a result, the sample mass or amount absorbed is going up. The desorption branch can be explained by this reducing the relative pressure from 90 to back to 0 as a result, whereas the amount of adsorptive adsorbed is decreasing. So this is typical adsorption-desorption isotherms, and the gap between adsorption and desorption is called hysteresis. Now, the desorption isotherms were actually classified into were grouped, and we look at the new classification on the right and the old classification here on the left. So we're going to go briefly to the old. When you have the 6 type of adsorption isotherms, so we can have microporous, which are typical type 1 isotherms. So they are typical for microporous solids having relatively small external surfaces, and the limiting uptake is governed by the accessible micropore volume rather than by internal surface area. Then we have the non-porous type 2 isotherms. So it is reversible isotherm representing monolar multilayer adsorption for non-porous materials. Type 3 is for big substrates with unlimited multilayer formation process. Type 4 and 5 is interesting for us. So this is typical for adsorption of mesoporous solids. Proceeds by multilayer adsorption followed by capillary condensation, resulting in type 4 or type 5 isotherms. Characteristic features of these type 4 and type 4 isotherms are the hysteresis loops, which are associated with capillary condensation taking place in mesoporous, and the limiting uptake of a range of high POP naught. Okay, so now we've done this the theory for adsorption size. So now how can we obtain the physisorption data that can be used actually to characterize the catalyst? So there are two main techniques to characterize the catalyst. One, I call it the physisorption data. One is volumetric gas adsorption apparatus, which is typically used for BET or porosity measurements. The second one is gravimetric gas vapor adsorption. I mean, the main difference between these two in volumetric, we're looking at we measure the pressure changes. So once you dose the gas of or adsorptive of interest like nitrogen, you wait for pressure to equilibrate. And in the case of gravimetric, we actually continuously weight the sample during changes in concentration of gas or vapors around the sample. So I'm going to mainly focus on the rest of the talk on talking about the gravimetric vapor gas option analyzer, in this case DVS vacuum. So the DVS vacuum measures the uptakes and loss of vapor by material using balance at constant temperature and variable pressures up to 1000 torr, allowing absorption behavior to accurately determine. Now, what we're looking at here, on the right-hand side, we have the picture of the DVS vacuum analyzer. On the left-hand side is a scheme of the DVS vacuum. So let's go briefly. So what do you have the DVS? One of the key benefits of these gravimetric vapor absorption or gas absorption studies is that everything is under thermodynamic equilibrium, which is achieved by the temperature enclosure or incubator operating in the range 20 to 70. So this is a typical range. We can generate full POP knowledge for organic solvents and water vapor outside of the set of the pumps. Now, when you look at the more in detail here, what we have here, the other striking difference is that this system does not require carrier gas process operation. So we use the vacuum as driving force for the molecules to travel across the sample. So what it means, in this case, we will look at the water CO2. So we can connect water flask filled in, we can connect flask filled in with water to MFC1, and MFC2 is connected to gas. Now, the vapors are generated by liquid itself at thermodynamic equilibrium. So in a typical experiment, we pull the headspace of the liquid over the sample, and we measure the amount of absorbed or dissolved, depending whether we're stepping up or stepping down the pressure. Now, under the dome here, we have ultra balance. And for the balance, we have suspended two hang-down wires. On the left-hand side, we have the sample side. Right-hand side is reference side. This is the symmetrical balance, and as you can see, there's also symmetrical flow coming over the sample. Now, around the sample side, we have high-temperature preheater, which allows to heat up the samples up to 400 degrees under high vacuum. Reference side is used just to counterbalance when we go over the masses over 150 milligrams, because the balance is capable of lifting up to 1 gram of sample masses. Now, the system measures the absolute pressure using two transducers. And our exit side, we have the butterfly valve. And outside of the chamber, as you can see here, you have the turbomolecular pump and rotary pump here, another pressure gauge. So this is a typical system which is used to collect dynamic or static gravimetric vapor absorption measurements. So in a typical experiment, we load the sample and we measure and we flow the gases or vapors over the sample, while we maintain the pressure constant using the butterfly valve, which continuously receives closed loop feedback from the baratrons. And depending on the pressure, set pressure, it tries to maintain the set pressure by opening or closing of the valve, which actually regulates the amount of the sorbate molecule inside the chamber. Okay. Now, look at the inside of the instrument, which is actually quite important. So now to load the sample, you just undo these two clamps, this drops down, and you get access to the sample like in TGA. Now, so you have just this baratron, but what is important here, I want to show you. So this is the solvent reservoir. So this is the water, which is connected directly to the mass flow controller. And the second MFC is connected to the CO2. So this is very important that we're using the vacuum. So we take the headspace, which is flow over the sample. So this is solely water vapor absorption. Now, this setup is also important, which we're going to discuss later, where we're going to show the co-absorption data. Then you have one MFC connected to water, one CO2, and we're going to mix these two streams, gas streams, together in different flow ratio and collect the isotherms. Look at the absorption, to look at the behavior of the catalyst during the CO2 hydration reactions. Now, so how this DVS works? So initially, as I said, you load the sample. Once you load the sample into the metal pan, we pull high vacuum, high temperature, we outgassing the material completely. We completely clean the surface of the sample and we empty the pores. And when we do that, what we observe, so here we have a solid red line, which represents the mass data. As a result, during this outgassing stage or drying stage, we observe the mass loss. Now, once the sample is cooled to absorption temperature, let's say we go from 400 to 25 degrees, we introduce the water vapor. So the water vapor pressure is shown by solid blue line. And the way we do it, so we go from 0%, let's say, to 0.1%. As we do that, so downstream will be closed. We open the mass flow controller to fill up the chamber with this amount of the water vapor. And once we reach the set pressure, the both upstream and downstreams are open. So we're going to get continuously flow of water molecules over the sample while we continuously record the changes in the mass. So as you can see, this is very important because traditionally in volumetric system, this is done in the static method. When you just inject molecules, I wait for the equilibrium using the Brownian motion, whereas here is the flux of the molecule. As we do this, we continuously flow the molecules over the sample. What we observe, because we go from 0 to, let's say, 0.1% RA, we observed mass gain as a result of the sample taking up the water molecule or absorbing. And this mass gain is clearly visible here by the solid red line here. Now, as we step up the concentration of molecules or absorptive molecules, the mass of the sample going up, all the way up to 90%. Now, from this, so as we go up, so this is called absorption. When we step down, the concentration or the pressure is called desorption. Now, from these mass equilibrium points, at each relative pressure, we can construct the isotherms, what we can clearly see here. where the line in red is absorption, the line blue is resorption branch, and then you have the small hysteresis gap. Now, the equilibrium points at different pressure steps can be reached in time mode or mass equilibrium DMDT mode. So most of the time we can collect these data in DMDT mode when we set certain equilibrium threshold value, and when this threshold value is met, software automatically goes to the next stage. The systems allow you to collect very important in situ drying curves, or which can be obtained or outgassing curve, real-time absorption-desorption kinetics, as showed before, absorption-desorption isotherms. So from the kinetics data from mass equilibrium points and different mass equilibrium at different relative pressure steps, we calculate the isotherms. We can also collect the absorption-desorption isobar. What it means, we keep the temperature. We vary the temperature, but we keep the pressure constant. And from the isotherms, we can collect the three different temperatures. We can calculate heat of absorption, and from the kinetic diffusion coefficients. Now, so gaseous characterization. So let's first discuss the volumetric data. So here, look at the nitrogen absorption and desorption isotherms on the left-hand side of pure silica aerogels and different loadings of nickel nanoparticles into silica aerosols. So both nickel nanovials isotherms show type 4 isotherms and hysteresis loop H1. So the isotherm, the type 4 isotherm indicates mesoporous structure, and hysteresis loops indicates that catalyst has narrow range of uniform mesoporous. And this is also in agreement with SEM images which you showed earlier. So SEM images shows a very that more materials got actually mesoporous supports. In the table here, we look at the surface area of all these catalysts, pore volume, and average diameter. So now let's move to the gaseous characterization using gravimetric vapor absorption technique. So here we're going to look first on the vapor absorption data. So on the top line here shows the kinetics. So what we see here, solid red line is changes in the mass, and solid blue line shows the changes in the relative pressure. So what we see here in all three cases, we step up the relative pressure from 0 to 90% and back to 0. So these are the full absorption-desorption cycles. Well, what we can see at the bottom line shows the respective absorption-desorption isotherms, which we calculated from the kinetic data above. So all vapor absorption isotherms indicates high interaction between water vapor molecules and catalysts. So the absorption process can be described by water absorption on surface functional groups, followed by the formation of cluster of water molecules on existing water molecules, and pore filling around 50% POP naught. So when the pressure is high enough, and the pores are completely filled, a plateau is reached. We also observe formation of hysteresis loops for all three samples because of capillary condensation and formation of irreversible hydrates. Now let's look at the carbon dioxide studies at 25 degrees. Again, top row shows the kinetics for carbon dioxide absorption up to 1 bar, and the plot below shows the absorption-desorption isotherms. So what we can see here, again, the absorption and desorption curves are almost identical. The process is reversible. So desorption curves are to the same point at the start of the analysis. There is no hysteresis loops observed, indicating no tensile strength applies to the pores. So they are, and what you can see, the pure silica gels shows the highest absorption capacity for carbon dioxide, followed by the nickel nanowires particles, and then 700 ppm nanoparticles, and nickel nanowires particle and nickel nanowires. Now we're going to move to the co-absorption studies when we wanted to see actually the behavior of the the performance of the catalyst in the presence of the water and CO2. So first observation, what we can see that the absorption-desorption behavior is very similar to the water absorption isotherms. So all isotherms have open loop hysteresis, as you can see for both silica aerogels and silica aerogels nickel nanoparticles or silica aerogels nickel nanowires. And all of the samples basically suggest that all samples retain the water. And one thing is nickel nanowires actually retain the water the strongest, as you can see from the hysteresis loops, because on the desorption bond, because on desorption branch, the curve didn't return to the same point of the analysis. Nickel nanowires and nickel nanoparticles show the higher absorption capacity compared to silica aerogel. We can also conclude that the catalyst activity is strongest for nickel nanoparticles, followed by nickel nanowires and silica aerogels. And this is determined by looking at the changes in slow body isotherms. Now, so these are results of the analysis. So let's move to the conclusions. So we can conclude that we successfully synthesized mesoporous silica gel doped nickel nanowires. Also the hydration tests or Aqueous characterization revealed that nickel nanowires, silica aerogels, catalyzes CO2 hydration reaction, which was demonstrated here. So with the highest loading of nickel wires for this strongest catalytic reaction. And DVS analysis, this will confirm that nickel nanowires show enhancing of the catalytic activity for carbon dioxide hydration reaction when compared to nickel nanoparticles, which is demonstrated by this plot here. Now, just again to acknowledge my colleagues at Sulfur Measurement Systems, my collaborators at Newcastle University, and we also would like to EPSRC for the financial support and grant. Now, I would like to all thank you for all your attention, and floor is open to any question you might have.
Yes, we now invite the audience to submit any questions they may have for the doctor in the panel to their right, please. If I could just get the ball rolling, Vladimir, could I ask if there's any particular need or query that that caused you to explore this topic in the first place?
Oh, that is I think one of the main needs was to explore to actually improve the catalytic performance of the existing catalysts and also the ability actually to use employ the readily available silica aerogels for this kind of reaction. So we just want to use more natural materials.
Great. We have a question from Claudia Arnold. He asks, how large can the sample be? Can technical granules be tested as they
are? In terms of the sample sizes, is actually, if you look at so we typically use about 30 milligram of sample for this kind of the tests. We can use the pellets. As you can see here, we can hold the pellets, as you see here, or hold the beads. So there is no really limitation to the sample sizes. The sample size is mainly limited by the opening of the sample chamber. So if you don't work with the powder pellets, we can load the whole film or whole composite and hang it directly. So the main criteria is actually the size of the base of the sample. So typically it's 30 milligrams for measurements.
A question from, a question from Dr. Remy Gillette-Nicolas. He says, thank you for a nice presentation. And he asks, you showed a few open isotherms, and I don't think it is related with a real hysteresis, but rather an equilibrium effect. how do you make sure the data is properly equilibrated?
Oh, thank you very much for a very good question. I mean, we are the equilibrium, since this is gravimetric wave absorption collections. So we can actually see the equilibrium, we can visualize the equilibrium points, and the equilibrium points was determined by the threshold values for the measurements. So these threshold values is typically determined by the user or by the samples, and I agree, in this case we use equilibrium point that if the change in the mass is below 0.003% per minute for duration of the 10 minutes, the software automatically goes to the next stage. Okay? So this is the equilibrium criteria used for this experiment. Now, if this equilibrium criteria was not good enough, we can lower the equilibrium time value threshold, or we can increase the time for stability duration. So I agree that if you don't have the good equilibrium points, then you would get a larger hysteresis. But in this case, because we also form the hydrates, as a result of the formation of the hydrates, you get a bit of the hysteresis. So one of the benefits of the gravimetric system is that you can visualize the kinetic, which shows the equilibrium points, and you can also see whether you are in the equilibrium. And as we've shown previously in the kinetic data, most of the data were in equilibrium. But bear in mind, maybe because of the way it is plotted, it doesn't seem it's in equilibrium. But in terms of the threshold, what we said, we met the threshold. If there is need to increase the threshold, that's not the problem, and we can use even more rigid equilibrium criteria.
Thank you. Another question here from Claudia Arnold. She asks, during co-adsorption, can you distinguish between the adsorbates?
In dynamic mode, it's very difficult to distinguish between amount of absorbed water and CO2. And the reason is because we measure total uptake by sample. Okay? And the total uptake contains contribution from both carbon dioxide and water. In order to distinguish amount absorbed from CO2 and water, we need another measuring device which can tell us how much of each is absorbed. Now, there is the other way to look at it. That was no purpose of this because you wanted to do it in the flow system. The other way to look at the co-adsorption is that you can do it in the static mode, that you actually preload. You equilibrate the sample with certain concentration of the water vapor. Then you bring CO2 on top of it if you have the right type of the materials. And this way we can determine the amount of CO2 absorbed at a constant loading of the water vapor. I agree there is a few assumptions to be made, but this is the most straightforward and easiest way to see the performance of the materials when we perform the co-adsorption measurement. Because one thing I recently did the data, actually not necessary when you preload the sample, let's say with 1% RH, and then you bring the CO2 on top of it up to 1 bar, it does not necessarily mean that your mass is going to go up when you increase the pressure. What I observed is actually the mass was going down. So if you have the chemisorption, some reaction takes place, you can actually determine from the static measurements whether you actually have the physisorption, chemisorption processes, or whether we're actually absorbing the CO2 or not. So if you are really interested in determining the amount of each absorbs, you have to go to use either static method, or the other option is to use, for dynamic method, is to employ the ideal adsorption theory simulations, where we're going to use pure adsorption isotherm of water and CO2, and then the composites and then the mixtures. And these isotherms are then used to feed the data in order to predict the amount of each adsorbed. And then the mixture of water CO2 experimental data then compared with the simulated data. That's the only way to do it. Another option we're looking at now at the moment is whether we could actually use FTRI or other techniques to actually do it simultaneously in order to determine the water CO2 amount of water and CO2 at the same time.
Thank you. Question here from Vissam Fortas. They ask, to what degree can carbon dioxide increase the temperature?
I'm not sure I understand the questions. I mean, we can
perhaps we give Wissam the opportunity to unmute his mic and ask and pose a question himself. He may be able to pose it better than me. Wissam, if you would like to unmute yourself and ask the question directly to Dr. Vladimir, please do so. Well, so the question is typed as, to what degree can carbon dioxide increase the temperature?
I'm not entirely sure I understand the question. So in our system, we can work gas adsorption isotherms only up to 1 bar in the temperature range to 20 to 400 degrees.
Okay. We have another question from Dr. Remy. He asks, can you use aggressive gases in the instrument, such as hydrogen sulfide? And how many vapor sources can we use simultaneously?
So first answer to the first question, yes, we can use the hydrogen sulfide and let's say SO2 as well, or ammonia. So we can use most of the aggressive gases in the system. As you saw, so we have the two mass flow controllers, so you can use the two vapors at the same time. So you can have the water and xylenes or water or benzene or any vapors, or you can have two gases. Now, you can also do three components that you could have basically CO2 or H2S mixed with nitrogen, and on the other MSC, you can have the solvents of your choice. So at the moment, you are limited 2 or 3 composition maximums to measure the vapor absorption or gas adsorption isotherms.
Great, thank you. And Wissam has resubmitted his question now. He's reposed it as, to what degree can the carbon dioxide increase the temperature of the samples?
Oh, so it's really, we haven't observed any increase of the sample temperature in this experiment, but when you, in the past, I saw in some of the experiments, some sample could be increased, sample temperature, especially when you work with the water, could be increased by 2 or 3 degrees. In the case of carbon dioxide, we haven't seen any temperature changes during the measurements.
Okay, great. I think that is all the questions we have for today, but if anyone does have any further questions for Dr. Martis, please do feel free to send them through to marketing@surfacemeasurementsystems.com. Remy's had one final question. Do you have time for this, Vladimir? We'll get this in.
Yeah, sure, yeah.
Yeah, perfect. He says, SMS has a history of allowing IR probes to be coupled with DVS instruments. Is this a potential option for the DVS vacuum?
Not at the moment. I mean, if you want to measure just the temperature of the sample in situ, that's possible to couple. But if you wanted to measure infrared, yeah, no, at the moment we cannot use we can only measure the temperature using the infrared, but we cannot measure actually infrared data in DVS. It's not the option at the moment. Also, no, you won't be able to use a preheater if you're going to go for IR. So this will actually limit your operating temperature down to 50 degrees only.
Right. And a final question from Vissa. He's asked, is DVS analysis more important or valuable than DSC analysis?
Oh, I think this is a very good question. And the answer is both analyses are very important, but the DVS analysis is driven by the applications and use of the material. So if you work in a field which requires to understand the absorption behavior of the material, or you try to use the material in distillation columns, or you try to determine or you're designing new chemical plants and you want to know how much heat is released, I would agree a DVS analysis will be more important. So as I said, this all depends on the application of what you're trying to understand. And DVS is usually one of the main application or characterization tools when you want to understand the behavior of the material in realistic conditions, because we never work. So yeah, I think the answer is basically it all depends on the application and what you're trying to do. So yeah, if it's really related to absorption science, yes, I would say the DVS is more important than DSC. And also, if the water plays an important role in your applications and it can have huge effect on performance of the material or performance of the system, yes, DVS will be more important than DSC.
Great. Well, I think we'll close things off there. Thank you again, Dr. Martis. Do you have anything final to add for our audience?
I just would like to thank you for our participants, and if you have any further questions, please don't hesitate to get in touch with us. So I'm happy to answer all your remaining questions.
Thank you, and I'm sure all our audience will join me in thanking you once again, Vladimir, for taking the time to give this presentation today. We once again invite everyone to submit any further queries or questions they have about this topic or our instruments to marketing@surfacemeasurementsystems.com. We have a few upcoming webinar sessions which we think you might be interested in. We are taking part in the Bion Innovative Cluster Innovation Coffee Series. That we will have a session covering characterization of synthetic and bio-based composites on the 11th of November. And from our North American office, Dr. Daniel J. Burnett will be giving a follow-up webinar to his poster session at the AAPS FarmSci event. So please go to our website, www.surfacemeasurementsystems.com, to find out more about that upcoming educational content, and we hope to see you all there. Thank you all again very much for joining us today, and I wish you an enjoyable rest of your day. Thank you.
Thank you. Bye.